Okay, so we talked about various kinds of nuclear reactions. We talked about compound nucleus reactions, we talked about direct nuclear reactions, in which transfer reactions, that is the stripping reactions or pickup reactions, capture reactions, scattering, elastic scattering, inelastic scattering, all these things we discussed, and little bit of mechanism and physics we discussed. These nuclear reaction had been the tools in the hands of physicists to know about the structure of nucleus inside and many other information. So, typically if we look at what kind of informations one gets from these reactions, one is to get the energy levels of a nucleus. Within that nucleus you have nucleons going into different shell model states, and then those energies of those things can be obtained from the kinetic energy and the angular distribution of this outgoing particles in a typical nuclear reaction experiments. So, let me work out that energy relation between energy of the outgoing particle and the energy level, excited energy levels of the nucleus. Okay. So, typically the nuclear reaction would be something like this. You will have a target, we have discussed this geometry several times, and then some projectile particle A will be bombarded here, and it will interact with some nucleus X here, and then it will convert this nucleus X to some nucleus Y, which will recoil inside, and it will generally be stopped here itself, but another particle B can come out at certain angle, and it is this B particle that we detect in the experiment. So, we put our detector here, and this angle is theta. So, we can vary this theta, we can put the detector at any angle we wish to get the angular distribution of these particles, and the detector also analyzes energies, that means the particles B particles which are getting into the detector. So, what is the distribution of kinetic energy there, with what kinetic energy they are coming. So, all those things are the experimental data that we have. Now, I show it as a two dimensional picture. So, this is that X nucleus, initial nucleus, and this A particle going here. So, this is the initial condition with some kinetic energy K A and some linear momentum P A, and then after the reaction this X becomes Y, and this Y comes out, not comes out, it is in the target, but it starts moving in some direction, and this B particle is going in some other direction. So, if we call this angle theta and this angle phi, the kinetic energy of this particle is Kb, linear momentum is Pb, the kinetic energy of this nucleus here, the product nucleus Y. So, your reaction is X A B Y, right, that is the reaction. So, this product nucleus Y here is going in this direction, the kinetic energy is K Y and the linear momentum is P Y, and this one the kinetic energy K A and the linear momentum is P A. The linear momentum will have its own direction. So, if I write the momentum conservation equations and energy conservation equations, these equations would be, first let us write linear momentum. So, linear momentum in x direction, this direction of initial motion of this A particle is taken as the x direction. So, in this direction the linear momentum, initial linear momentum is P A. Remember, target is fixed in the laboratory, we are using laboratory frame. So, the kinetic energy momentum of this x is 0 in this frame, and therefore, the linear momentum is just P A in x direction, and that P A should be equal to the final linear momentum in x direction, and this will be the linear momentum of B, that is P B cos theta and plus linear momentum of this nucleus y. So, it will be p y and then cos phi. This is just after that nuclear event. After that, this y nucleus it is inside that target. So, it will collide with other nuclei and then it will stop and all those things will happen, but just after this reaction it has started in this direction with this linear momentum. So, it is this, and in y direction there is no initial momentum, and therefore, the total linear momentum in y direction should be 0 after the event. So, if I take the y components, we will have p b sin theta. So, p b sin theta, that should be equal to this p y sin phi. This should be p y sin phi. So, that in y direction the two momenta cancel each other and the resultant is still 0, which was 0 before the event. So, these are the linear momentum equations. Now, write the energy conservation equation, total energy before the event. So, total energy is mass energy, rest mass energy of A, rest mass energy of x and the kinetic energy of A. So, that is m A c square plus m x c square and plus k A. So, that is the initial energy before the event. This is the energy, the rest mass energy of this A particle, rest mass energy of this x particle and the kinetic energy of A particle, kinetic energy of x particle is 0. So, that is initial energy. Final again rest mass energy. So, this should be equal to m b times c square plus m y times c square. So, that is the rest mass energy of these two particles, and then the kinetic energy of B plus kinetic energy of y. So, k b and k y, and if this y nucleus is produced in an excited state, that extra energy also has to be written on the right hand side. If this y nucleus is produced in the ground state, then this is all. All these rest mass energies that we are writing, that is for the ground state, right. So, if everything is in ground state, this is the energy conservation, but then if this y nucleus which is produced because of this nuclear reaction and it is produced in its excited state, which is some delta E above the ground state. So, that extra energy delta E is also present here. So, plus delta E. Okay. So, this delta E is y nucleus, this is the ground state, let us say, and then when the y nucleus is produced, it is produced in this excited state. So, this is delta E. So, that is energy conservation equation, and from what are the quantities in these equations that are known to the experimentalist or which are measured in the experiment or are available in the books, in the tables, in the data. So, if you look at this energy equation, mass of A, mass of x, mass of B, mass of y, all these things are available in the data tables. If you know what are these nuclei A, B, x, y, these things are there. Then kinetic energy of particle A, since we are sending this particle A beam on the target nucleus, so we are controlling the kinetic energy of A. We have set how much with what kinetic energy we are sending this beam. So, Ka is also known in the experiment. This side Kb, B particle, the kinetic energy of B particle, that is measured in this detector. So, the electronics will do the job and will tell that with this kinetic energy a particle B has come. So, that can be measured, that also comes out from the experiment. Ky, this Ky is something which is beyond our reach, because this y particle is created inside that target and starts in that phi direction with kinetic energy Ky, and then all those collisions and other things, it never comes out. So, we do not have any handle on that. So, this is not known. So, if we want to know this excited state energy delta E from this experiment, I should eliminate this k y, and this k y can be eliminated using these two momentum equations, because k y is p y square divided by 2 mass of y particle. This is non-relativistic expression, but all these kinetic energies are in few MeVs, 4, 5 MeVs, 10 MeV, 1 MeV, and the mass of the nucleus is in 1000 MeVs, right. A single proton itself has 938 MeV or so, and therefore, this non-relativistic expression is perfect. Okay. So, we use this non-relativistic expression because the kinetic energy is small as compared to the mass of this y, and this p y I can get from these two equations, which are the linear momentum conservation equations. You can write from here p y cos phi is equal to p a minus p b cos theta, and the second equation is there, p y sin phi is equal to p b sin theta. So, you square these two and add, you get p y square is equal to p a minus p b cos theta square of it and plus p b sin theta square of it, which is p a square plus p b square and minus 2 p a p b and cos theta. You can write these p a p b in terms of the kinetic energies, because that is the quantity that we know, that we measure in experiment, and so this is p a square. What is this? 2 of mass A and then kinetic energy of A. And p square is 2 m k, or k is p square by 2 m. Then p b square similarly 2 m b k b and minus 2 times square root of p a into p b. So, p a is the square root of 2 m a, 2 m a k a, and p b is square root of this p b here is the square root of 2 times m b k b, and then cos theta, right. So, the kinetic energy of y particle k y, which is p y square and divided by 2 m y. So, divide this whole expression by this 2 m y to get the kinetic energy of y particle, and that will be divided by 2 m y. So, k a times m a divided by m y, that is the first term. Then second term is k b multiplied by m b by m y, that is here, and then minus. This 2 will cancel this 2, but then there will be another 2 from this square root expression. So, you will have 2 here and square root of m a m b, and if you write inside that square root, it will be m y square, then square root of k a and k b is there. So, k a is there, k b is there, and then cos theta. That is kinetic energy k y. Okay, come back to the energy expression, which is here. M a c square plus m x c square is the initial rest mass energy, and m b c square m y c square is the final rest mass energy. Take it to the left side. initial rest mass energy minus final rest mass energy is known as the Q value, you know that. So, Q is the initial rest mass energy m a c square plus m x c square and minus the final rest mass energy, that is m b c square and plus m y c square. This quantity is known as Q value of the reaction, and remember this Q value can be positive, can be negative, can be 0, because here we are not talking of spontaneous reactions. So, that the final rest mass should be smaller than initial rest mass. We are sending the particles with certain kinetic energy, maybe few MeVs of kinetic energy. So, even if Q value is negative, even if the rest mass energy of the final product is more than the rest mass energy of the initial product, the reaction can still take place. We will do the condition for that. So, this is Q value, and therefore, I will just write Q here, and that will take care of these 4 terms. So, on the left hand side it is Q and plus K A. So, I have taken care of these 4 terms and this K A, and then I have on the right hand side K B plus K B and plus delta E and plus K Y. So, for K Y I will be writing all that expression, that is plus then K A m A by m y plus K B m B by m y, and then minus 2 times square root of m A m B and K A K B divided by m y and then cos theta. So, you can collect all those K A terms together, K B terms together, you can take everything on one side if you so wish. So, you have let us take everything to the right hand side. So, you have K B here, K B, and then you have 1 plus m B by m y. So, I have taken this term, I have taken this term, and then let me write minus K A and then 1 and minus m A m y. So, I have taken care of this term and I have taken care of this term. Remember, everything is being taken to the right hand side. So, this K A comes here, minus K A it becomes. So, it is minus K A and plus this term. So, this is taken, and then this minus 2 times. Now, let me erase this right hand part. Okay. So, all these things have been taken, and then what is left? This term here minus 2 times square root of m A m B K A here and K B here divided by m y and cos theta. So, this term is written, and then plus delta E and minus Q. So, plus delta E and minus Q is equal to 0. So, let me check it once again. This is K B and 1 plus this, then minus K A, that is this. So, that, and then this minus 2 times m A m B K A K B by m y cos theta and plus delta E and minus Q, and that is equal to 0. So, in this expression, if I put all those known quantities, I can get this delta E. Right. The Q value will be obtained from the masses of those 4 particles A, B, X and Y. So, those masses are all tabulated. So, from there we can get that Q value, and other things, all other kinetic energies are known, K A, K B, then again masses, and here also K A, K B. So, and theta is measured. So, from this equation I can write what is delta E. So, for a particular kinetic energy observed in the detector, we can work out what is the excited energy level where this particle has gone. So, I will show you a simple calculation for this particular reaction 16O and then dP going to 17O. Of course, it will go to the excited state, you can put a star here. So, this is the reaction, that means this deuteron is made to incident on this oxygen target, and what we are observing is a proton, and inside the target you are creating that 17O. Right. So, this reaction I will show you an Excel calculation and how this comes, this can give you the energy levels of this 17O. All right. So, look at your screen. In this we are calculating excited state energy of for that reaction that is written there, and if you look at the quantities that I have written here, this is Ma. A is, what is A? A is here the incident particle, that is deuteron. It is mass in certain units. Deuteron you have almost 2 AMU, because you will have 1 proton and 1 neutron. So, mass of A. This is mass of B. B is proton. So, that mass is taken as 1. I am doing an approximate calculation to just show that these equations can be utilized and these data can be utilized to get the excited energy levels. So, mass of this B particle, that is proton, is 1. Then Y here is 17 oxygen. So, I am taking mass at 17, and then kinetic energy of A. So, let us take these deuterons being sent with a kinetic energy of 10 mega electron volts. So, 10 MeV. So, all these energies are in MeVs. So, kinetic energy of this A particle, that means kinetic energy of the deuteron is 10 MeV. Now, Q value for this particular reaction, which you can just calculate using the known masses of oxygen 16, oxygen 17, deuteron and proton, that Q value turns out to be about 1.96 MeV. So, this is 1.96 MeV. Now, this B kinetic energy of B particle. So, some value you have to take. So, some value you have to take. So, I am taking some value 11.69, close to what a particular experiment has measured it, and then theta. This theta that I am using here correspond, it is written here 0.436111, as you can see here. This is in radian, it corresponds to 25 degrees. So, what situation I have taken? I have taken a situation in which the detector is placed at 25 degrees from that incident direction, and then it is picking up the outgoing protons, and suppose the proton kinetic energy it has measured is 11.69. So, for the particles for which the kinetic energy is measured this much, what is the corresponding state of this Y particle? So, that calculation is shown here. All that expression that you have on your board. So, that is so all these values you can put there and then calculate the value for delta E, and that delta E turns out to be, for this particular number it is 0.03. In fact, it is the ground state, is 0, excitation energy is 0. So, if for corresponding to the ground state of 17O, the kinetic energy of these protons which are detected in the detector is something like 11.69. But the detector not only detects these particles of kinetic energy 11.69, it detects other particles of other energies too. So, what other energies are there? They are discrete. In fact, if you plot the cross section as a function of kinetic energy detected in the detector, kinetic energy of protons, you find that there are certain peaks. So, 11.69 was one, the other one is about 10.81, that is written here. So, one gets kinetic energy somewhere around 11.69 MeV, and then the other next peak comes out to be about 10.81. So, if I write 10.81 here, if I use 10.81 here, what happens? So, in place of this 11.69, let me replace it 10.81. So, now I write this and we see that the energy, this delta E has changed, right, which was almost 0, now it has 0.91 or so. So, if I get the kinetic energy of 10.81 MeV in the detector, from there I come to know that 17 oxygen, which I never observe in this particular experiment, right. The oxygen 16 was our target and deuteron was our projectile, and what we observed in our detector was proton. 17 oxygen was formed inside that target nucleus and we had no handle to look at that. But then from this data we know that 17 oxygen has an excited state at 0.91 MeV. So, the first excited state is 0.91 MeV. The next lower kinetic energy that one observes is approximately around this 8.58 MeV, and corresponding to this energy you can again calculate what is the energy of that 17 oxygen above ground state. So, what I have to do? I have to write here 8.58 in place of this kinetic energy of B particle. So, I can do that and 8.58. So, this is 8.58 and enter. So, what you see? You see energy of 3.1, something like 3.1 MeV. So, you have gotten, you are getting the energy level diagram of 17O. The ground state was there, then the first excited was at 0.91 and then the second excited state is here about 3.1 MeV. Similarly, you can go for this fourth one 7.77. So, you can write that 7.77 here. So, 7.77, this is the kinetic energy of the proton, and if you do that, it is somewhere else 3.88. These numbers are only to show you how you get delta E from the measured quantities. These are not the very accurate number of for that 17 oxygen, but this is how you make the calculations. Okay. So, I am coming to the board now. Okay. Now, from this equation that is here, this equation, you can do some more things. For example, you can think of threshold energy. What minimum kinetic energy of this projectile particle is necessary for this particular reaction. So, if you look at this equation and focus on this kinetic energy of B particle, you see that it is a quadratic equation in square root kb. So, square root kb square is there and then there is a term of square root kb, and then these are the so called constant terms. So, if you think in terms of quadratic equation, a x square plus b x plus c equal to 0, and for x you think of that square root of kb. I can write it little bit in that form. So, it will be kb times 1 plus mb by my, and then let me write this one. So, it is minus 2 times square root of ma mb and ka here divided by my and cos theta also, and then square root of kb, and everything else I will write here. So, it is minus ka, I can bracket here, remember this minus. So, ka into 1 minus ma by my, that is, and then plus q minus delta E, plus q and minus delta E. This is equal to 0. Right. So, that it is a standard quadratic equation format. So, square root kb square is there. So, ax square. So, this is ax square and then plus bx. So, this is in place of b and then x and then c, the rest of it. So, minus taken outside, ka 1 minus ma by my and then since I have taken minus outside, it is plus q minus delta E equal to 0. Now, the condition on K B would be that this discriminant should be first, it should be greater than or equal to 0. So, that you get a real value of K B. So, that is one, and also square root of K B should be positive, because square root of K B I am taking from linear momentum P B. P B I had written as a square root of 2 m B K B. So, if that be the case, linear momentum P B is positive. I have already taken cos theta, sin phi. So, directions are taken care. So, that P B is positive. So, root K B is positive. So, from this equation you can put conditions. First is that the discriminant should be greater than or equal to 0, that is one, otherwise the roots will be imaginary. So, that will put certain condition on K A, that K A should be at least this much, and then even if they are real, the quadratic equation has two roots, they are real. So, if one root is positive, one root is negative, reject that negative root and pick up only the positive root. There is certain range in which you have both roots positive. So, there are two kinds of kinetic energies of B particles are possible, but normally if the target is heavy and this incident particle and outgoing particle, they are quite light, which is generally the case in these nuclear reactions. In that case, that range is very small and you have almost 1-to-1 correspondence between the kinetic energy of K B and the kinetic energy K A. So, you can work out all these things and you can put up conditions. What you will find is, if this Q value happens to be positive, that means the rest mass energy of final products is small and rest mass energy of the initial products is larger, then there is no threshold, there is no minimum limit on K A, any K A will do. But if this Q value is negative, so natural, if Q value is negative, if the final products masses are larger than the initial one, then you have to provide certain minimum K A. How much that K A should be, that will come out from these conditions, discriminant greater than or equal to 0, and of course, it will also depend on delta E, which state you are taking in that final nucleus, which state you are taking that final nucleus in, and also the cos theta. So, it is not just the difference in the rest mass energies, because the linear momentum has to be conserved. So, certain kinetic energy will be present to conserve the linear momentum. So, that initial kinetic energy of K A particle should provide the increase in the rest mass energy, as well as together with that it also has to provide the kinetic energy needed to conserve the momentum, and that kinetic energy will also depend on theta. So, depending on theta, depending on the delta E, you can find how much should be that threshold K A from here. So, all these energetics, all these energy considerations one can work out, and that will be useful for analyzing the data obtained from the scattering data. All right. So, there is one more important phenomena related to this nuclear reactions, and that is known as resonance in nuclear reactions. Or nuclear resonances, sometimes it is called. What is this phenomena? So, let me take a specific example which we will be dealing in more detail in the next chapter, and that is, say, a neutron going to uranium-238 and getting captured there. So, it makes 239 uranium normally in excited state, and then it will decay through gamma emission. So, you can write this reaction as 238 uranium, and then your incident particle is neutron and the outgoing particle is gamma, and you are producing uranium 239 and maybe in excited state. So, if we look at this equation, we can work out what is its Q value. The masses of neutron and uranium 238 and 239 in ground state, they are all tabulated, and from there you can calculate the Q value. Q value will be mass of this neutron times c square plus mass of this uranium 238 times c square and minus mass of this 239 uranium in ground state times c square, that is Q value, and that turns out to be positive 4.86 MeV. So, let us work out its energetics. So, if this neutron going this way with certain linear momentum and then getting into this uranium 238, this is uranium 238 in the target fixed, that is before the event, and after the event this becomes uranium 239, and let us just take it excited state, formation of this uranium 239, later it will decay through gamma. So, the nuclear reaction event is this nucleus just gets absorbed here and it takes it to certain excited state of 239 uranium, right. So, it takes it here, this is delta E and this is the excited state it takes. Later on it will decay through this gamma emission and all that, but as far as the nuclear reaction is concerned, it is just this. So, it will move in this direction because linear momentum has to be conserved, and this is a simple story, no theta and other things, phi. So, it is linear momentum of this neutron, that is the initial momentum, and that should be equal to linear momentum of this uranium 239. So, that is linear momentum conservation. There is only a single particle. So, it cannot go anywhere else, it has to move in this original direction only inside the target. Remember, we are not assessing this nucleus, we are not reaching this nucleus, it is inside the target, but it has to start in that direction. So, this is one, and then we can write the kinetic energy, which will be kinetic energy of this neutron plus rest mass energy of this neutron and plus rest mass energy of this uranium 238 c square. So, this is the initial energy, kinetic energy of the neutron plus rest mass energy of the neutron and plus rest mass energy of this uranium 238. So, this is the initial energy, and that should be equal to the final energy, and that should be the rest mass energy of 239 u, that is 1 c square, and then kinetic energy of this uranium 239 and then delta E. Okay. That is the final energy. Finally, you have only one particle uranium 239. So, its rest mass energy, its kinetic energy, and also it is in excited state. So, that extra energy is there, it is in a higher energy state. So, this is the energy business. Once again, we can eliminate kinetic energy of this 239 uranium, because that is something which we have no control, and then all these rest mass energies I can put on one side and write it as capital Q. So, it will be Kn plus Q. So, this is Kn that I have taken and this Q I have taken, and this is equal to K of kinetic energy of that 239 uranium and plus delta E. And this kinetic energy of uranium 239, once again I can eliminate, and by writing it as this linear momentum of 239 uranium square divided by 2 times mass of 239 uranium. So, that is this K 239 uranium and plus delta E. Now, this is equal to linear momentum of this 239 uranium, it is same as linear momentum of the incident neutron, that you can see on this board. This P n is same as P 239 uranium. So, I can write this as P n square. Okay. P 239 uranium is same as P n, n is the neutron, incident neutron, linear momentum of that, divided by this quantity, and this I can write as 2 times m n here and m n here, and then divided by mass of 239 uranium and plus delta E. Okay. So, take this and this is kinetic energy of the neutron. This is kinetic energy of the neutron, and then m n divided by mass of 239 uranium and plus delta E. So, what you have? You have K n common 1 minus m n by m 239 uranium. So, I am taking this to the left, this I have taken to the left here, and q I will take to the right. This is equal to delta E and minus q. Okay. So, if you send a neutron with almost negligible energy, k n close to 0. So, if k n close to 0, then delta E is equal to q, right. So, if you just send a neutron with almost 0 energy, then delta E will be equal to q, and that will be 4.86 MeV. Whatever q, I am writing here in 2 decimal places, 3 significant digits, whatever is the value of q for this reaction, this almost 0 energy neutron, if it is absorbed, it will excite this uranium 239, the nucleus, final nucleus that is formed by capturing this neutron to the energy level close to 4.86 MeV. Now, where is that energy? Is there an energy there? Because a nucleus will have discrete energy levels. So, I just cannot demand that excite at this particular energy. So, if the nucleus here, this uranium 239 nucleus, it has got its own energy levels, right. So, at 4.86 there may be a level, there may not be a level. So, but this energetics says that if this reaction is to take place, this should be delta E, and then depending on what kind of kinetic energy I am supplying. This neutron, if neutron kinetic energy is 0, it is this, but otherwise this delta E will be q, that is 4.86 plus k n times 1 minus m n by mass of 239 uranium. Depending on what kind of k n I am applying, what kind of kinetic energy I am giving to the incident neutron, that particular level is to be populated. But then if there is a level there, then it is perfect, and then this neutron will get absorbed there. Now, the probability of its getting absorbed there will be high, and if there is not a level at that particular delta E, then this reaction will have low probability, because all these energetics have to be satisfied. So, if you look at the variation of cross section of this reaction, which is related to the probability of this reaction, which means the probability of this neutron getting captured by this uranium 238, that will have large values for certain kinetic energies, which will match these energy levels that exist, and if they do not match, the probability will be low. So, if you do a plot where this is the incident kinetic energy of neutron, and here you are looking at the cross section, sigma of this reaction, then at certain energies the reaction will be very high, the reaction probability will be very high, and then it will drop, okay, like this. What these peaks correspond to? These peaks correspond to energy levels of uranium 239 beyond 4.86 MeV. There may be levels below that will not be populated by these neutrons, because even if the neutron kinetic energy is 0, the delta is 4.86 MeV. So, depending on where are those levels beyond that 4.86 mark, and they are discrete. So, there are certain values, discrete values, where you have the values of delta E coming from this energy level scheme of uranium 239. So, for those particular levels delta E, you will have corresponding Kn, corresponding kinetic energy of the neutrons, where the probability of its getting captured, probability of this particular reaction to take place will be very high. And then if you send the neutron with little more energy or little less energy, the probability will be low. There will be other reaction, scattering and all those other reactions can be there, but this particular capture, this particular reaction where neutron is going into uranium 238 making it uranium 239, that probability will be low. So, this phenomena where the cross section suddenly increases at certain energies, certain kinetic energy of the projectile particle and drops, this is known as resonance. Okay, so, this is known as resonance, and it plays very important role in our fission reactors and some of the astrophysics nuclear reactions and so on. The shape of this line has been worked out theoretically. It is known as Bright-Wigner formula. It is kind of Lorentzian, and this width here is related to the lifetime of that particular state in that uranium. So, larger the lifetime, more stable is that state and narrow will be the width. So, this is resonance reactions. These are examples. This is an example of nuclear resonance reactions in which the cross section resonantly increases at certain energies, where the energy available for excitation matches with the actual energy level difference in that particular nucleus. So, if it exactly matches, it goes up. So, that is all about nuclear reactions, and next lecture I will go in another topic, and that will be nuclear fission reactions.